So here we go. Pre-calculus, right? Writing equations, given graphs. Let's take a look at a couple of these graphs. And in fact, I'm going to go ahead and make these bigger, if you don't mind.
Okay.
Because we'll just do them one at a time and spend a little bit more time looking at them. So let me open up this Jamboard a little bit bigger. I've got to go on my computer real quick and edit these things. We're on page 8. So I'm going to duplicate this slide a bunch of times and we'll just clean up the graphs so that it's easier to see. 5. Okay. So unfortunately, they don't let me crop this, but what I can do is make this as big as I can. And then on your computer, I'm teaching you little tricks here. You can put a rectangle in there and make the line of the rectangle white as well, so that it covers it up. You're kind of manually cropping it. Okay, so there's the first one. The next one is this one. And crop that. The next one is down on the bottom here. Now this one looks like a absolute value function, right? Might as well talk about them while I'm cleaning them up. So that number 7 looks like is an absolute value function. Can you recognize that?
Yes.
Okay. How about number 8? What kind of function is number 8?
Linear.
Yeah, that's just a line. So that's actually really easy, right? You don't even need to do transformations.
Yeah.
Are most of these things, are they talking about transformations, or are they not? Is that not necessarily what you have to do?
No, yeah, they're talking these ones are,
And then this is the last one. And can you tell what kind of function that is? Are you able to identify that function?
um
Can you tell what kind of function it is? Can you tell by even the labels on it? That's called a trig function. It's a trigonometric function. It's a sine or a cosine function.
okay.
So let's do that one last, because
Okay.
that one you probably don't, maybe you don't even know how that works.
No.
But this one, you hopefully can identify, see how there's a vertical asymptote?
Yeah.
When there's a vertical asymptote, and it looks kind of like a exponential. It's actually not an exponential, it's a logarithmic function.
Okay.
So log functions are, so what do they want? They just want you to write the equation of it.
Yes.
So your base log function, the log of x, y equals the log of x, looks like this. It's got a vertical asymptote as the y-axis, and it goes through the point 1, 0, and it approaches it here, and then it goes off this way. And what that is that's actually the inverse of the exponential function. If you remember what an exponential function was,
Yeah.
and the exponential y equals 10 to the x always goes through 0, 1, and it goes up like that, and it goes down toward this horizontal asymptote.
Yeah.
So these graphs are the inverses of each other, basically.
Okay.
If you flipped it over the line, in fact, I could have drawn it on here. I should have. If you flip it over the line y equals x, those graphs are they're reflections of each other.
Mm-hmm.
So that's y equals 10 to the x. Okay, do you remember that? Have you learned that?
Yeah.
Okay, so I'm pointing that out because when you see this immediately, what you should do is recognize, oh, wait, look, there's a vertical asymptote here. Oh, that kind of looks like an exponential, but it's a sideways exponential.
Mm-hmm.
So, but you also notice that it's flipped. Instead of going to the right, it's going to the left. So that means it's flipped over the line. It's flipped over the y-axis. You remember how to flip things over the y-axis?
Yeah, you make it negative.
What, the x or the y?
the y. Or sorry, the x.
So if you can't remember, I always just think of x squared. We all know what x squared looks like, right? It's a parabola.
Yeah.
If you make the y negative, in other words, if you make it on the outside, it's going to flip it. It's going to flip it down, right?
Mm-hmm.
So that would be flipping it over the x-axis. And so you're right. If you make the inside negative, it actually doesn't do anything to it because a negative x squared is still just x squared.
Okay.
And so you would have that same function back. So in other words, you're right. To flip it over the y-axis, you make the x negative. So my original function, the problem is they didn't really tell us what the function is. So it's kind of hard to know what it would be, but I'm going to guess, see if you can find what this point is way over here to the left. If you can count it, that's how you can tell what it actually is. 1, 2, 3, 4. Oh, actually, no, we can. Yeah, no, it always goes through here. That's like that point 1 over. It's like the point that's 1 away from your asymptote. Look over here at my original graph. You see how this point is 1 away from the asymptote?
Mm-hmm.
So that's 1 away from the asymptote. Here's your asymptote, and that's 1 away from it. But then it's, if you look at it over here, if you look at what this point is right here, it kind of tells you what the base is of it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I believe that means it's a base 3.
Okay.
Base 3 or base 9? I don't know how picky they want you to be. I think it's a base 3 function. So your original function was going to be log base 3. Actually, it might not even be exactly 9. It might be base e. Have you talked about e yet?
Yeah.
So maybe this is just an ln function. Let's hope it's just a natural log function.
Yeah.
So your base function is the natural log of x. Is that what your teacher told you to use always for logarithmics? Just the natural log?
Mm-hmm.
Yeah. Okay. Well, there you go. So that's a natural log function, but notice that it's shifted. It's flipped over so that x is going to be negative, like you said.
Mm-hmm.
But then it's also shifted over 1 to the right, and it's shifted up because normally it would be here. This point would be here. Well, it would normally be here, but it's shifted. So we first flipped it so it would look like this. But then we shifted it 1 to the right, everything 1 to the right, and we shifted everything up 1, 2, 3. So it's going to be a negative on the inside, and it's going to go up 3. So I'm going to put a plus 3 on the outside, but now this is the tricky part. And I'm wondering how your teacher taught you to do this. But if I'm going to put this inside with the negative x's on the inside, and I want to move it 1 to the right,
Mm-hmm.
I actually have to put a plus 1 in here.
Oh yeah. Mm-hmm.
Did she explain or he explain why
Yeah,
that is?
Yeah, because the negative x.
When you make the x negative, you also have to do the opposite of what you would think with the shift.
Mm-hmm.
So shifting to the right normally would be subtracting 1, but you're going to add 1 to it.
Yeah.
Should I explain that more, or does that make sense?
No, I get that. Yeah.
Okay. So here's the way you can always check it. So I always like to, when I think I'm done, I always just plug in some values. So when I plug in 0, I should get 3, right?
Yes.
So when I plug in 0 for x, I get the natural log of 1 plus 3. And what's the natural log of 1?
1,
It's 0.
0. Okay.
Natural, any log base anything of 1 is 0. Remember this formula, log base b of 1 equals 0. And that's because anything to the 0 equals 1. You remember how these are related to each other? The equivalence?
Yeah.
Anything to the 0 equals 1 is the same as saying the log base b of 1 is 0. The log base anything of 1 equals 0. So that checks out, but let's try another point. Let's try let's see. Let's try -1. Let's just put -1 in here and see what we get.
Okay.
Because you can see it on the graph what it is. Oh, and then I realized that something's not right, because what I have is then I would have, oh no, that's right. So if I plug in -1 for x, that's going to become a +1, right? Because it's a -1,
Yeah.
which becomes a +1. So this is just the natural log of 2 plus 3. And if you punch that into your calculator, the natural log of 2 plus 3, natural log of 2 plus 3, you're going to get 3.69, 3.67 or something like that. And if we look over here, that looks like it's perhaps correct. Actually, it doesn't quite look, it looks like it's less than that. Looks
Yeah.
like it's 3 point something. So to me, it looks like it's stretched a little bit. In fact, my guess is that it's stretched by a factor of 3. And again, the reason I say that is because normally, let's look back at our original graph. This value right here, up here, this value would normally be just whatever that number was. When you go over 1, that number tells you what you had started with, because this is like saying 10, like for this is 10. 10 to the first power is 10. So this number, this actually, if it was 10, it would actually be more steep than this. This red graph would be a lot more steep. So at right here, that point would be 1, 10. Do you follow what I'm saying?
Yeah.
So when I plug in 1 here, I'm going to get 10. So if I were to go up 1 from here, I would expect it to be, you know, this distance right here would be E, if that's my base. And it's not E. It looks like it's 3 times as big as that. When I go 1 away from this and then go over here, it's taking me a lot longer to get there. Or it could be that it's just a base 9 graph or a base 10 graph.
Yeah.
That's why it's kind of hard to tell with these ones. You can't really tell because you don't have exact values on here. So this point way over here, this point way over here is the one that would tell you. All over here to the left, you see where I'm at?
Yeah.
That point, wherever it touches there, is kind of what helps you know what the base is. It's 1 away from it, and you go see how far it takes you. And so it looks to me like that might be a base 10. Maybe this is just log base 10 instead of ln. Maybe it's just log.
Okay.
But if your teacher said it's always log base e, I don't know. But I think it could be just this. This could be your answer.
Yeah, that makes sense.
Because now when I plug that number in, you're still going to get 0. You're still going to get 3 here because the log base 10 of 0 is still 0. I'm sorry, the log base 10 of 1 is still 0. So you're still going to get this point here. But when you plug in -1 right here, you're going to get the log of 2, not the ln of 2. And the log of 2, so if I did the log of 2 plus 3, that's going to be, see how that's a much smaller number, 3.3. Shouldn't say a much smaller number, but that looks about right. 3.3 looks about right. That point looks like it's at -1, 3.3. In other words, I just stretched out, making that base bigger, base 10 instead of base E. I kind of like stretched out this graph a little bit. I don't know. Does that make sense, or did I confuse you a little bit with that?
No, it makes sense.
Okay, so sorry about that. That was a tough one to start with, but
Yeah.
this one's a little bit easier. You can tell what this one is, yes?
Yeah.
What is this graph? What's it look like?
Isn't that a cubic? Oh,
Yeah, it's not a cubic, it's a cube root,
okay, yeah.
right? So your cubic, you're right. If you had a cubic, the inverse of a cubic is a cube root.
Mm-hmm.
So if I had a cubic graph, again, I don't know how much to get into this because I don't know how much detail your teacher wants. I have a feeling they just want kind of a general idea and it doesn't have to be exactly perfect. But if you took a cubic, it's that same concept we just talked about. The cubic graph would look like this.
Yeah.
But a cube root graph is the inverse of that. So if I were to draw a line, here, let me redo this a little bit because that's not quite right. Remember, a cubic graph goes through 1, 1,
Mm-hmm.
and it goes through -1, -1.
Yeah.
You understand what I'm saying?
Yeah.
So if I were to take the line y equals x, which is actually going to go through these 3 points, all 3 of these points, and if this red graph, the cube root of x is going to be flipped over that. So it's going to be like this.
Okay.
Do you see what I'm saying? Do you
Yeah.
see how this is a reflection over this line?
Mm-hmm.
The black graph and the red graph are a reflection over the yellow line. The yellow line is y equals x. That's how you find inverses. So that's what I have here. But notice this one on my graph is flipped. See how it's flipped? So it's flipped like this. So that means it's flipped over the what?
X-axis.
It's flipped over the x-axis. So what do I make negative?
The Y.
I make the x negative, don't I? Oh, you're right, the y. You're right. Sorry.
Very good.
Oh, the other one was flipped over the y-axis.
Mm-hmm.
Yeah, so that one's flipped over the x-axis, which means I make the outside of it negative. And now where is it shifted? Instead of being at 0, 0,
It's at 1, 2.
so it's 1 over and 2 up.
Yes.
So 1 over would be -1 on the inside, and 2 up would be +2 on the outside. Make sense?
Yeah.
And then how can you check it? Remember what I told you always to check it? Take some points you can see. Do you see this point? 0, 3.
Yeah.
So if I plug in 0, I better get 3.
Mm-hmm.
What's 0 minus 1?
-1.
What's the cube root of -1? Still -1.
Okay.
And then what's negative -1?
1.
+1. What's +1 plus 2?
3.
There you go.
Mm-hmm.
Okay. If I plug in 2, I should get 1. If I plug in 2, I would get 2 minus 1, which is 1. The cube root of 1 is 1. -1 plus 2 is 1.
1.
I know I did it right.
Yeah.
Okay.
Yeah.
This one is easier. This is just absolute value, yes?
Yeah.
So how do I do absolute value graphs?
They're in the what are they called? The the absolute value like lines.
So the trick for this one is you'll want to look at the slope. You see how the slope of this one? See how I go over 3 and up 1?
Yeah.
So my slope is 1 divided by 3. Rise over run is my slope. So it's really shrunk. It's compressed vertically. Instead of normally your absolute value graph goes like this, it's usually 1 on each side, right?
Yeah.
Rise over run, but this is this, so it's kind of like being compressed. In other words, you're multiplying by 1/3 on the outside.
Mm-hmm.
Get how I came up with that?
Yeah.
And then you're shifting, instead of starting here at 0, 0, you're shifting right 1 and up 2. So right 1 on the inside is a +1, yes? Whoops, nope, not a
Negative
+1,
minus.
a -1. And then up 2 is +2 on the outside. And how can I check it?
You can plug in the points.
Yeah, find a point that's easy to tell. See how it's 4, 3?
Yep.
So 4, 3, yeah, look at this. 4 minus 1 is 3. 1/3 of 3 is 1. 1 plus 2 is 3.
Mhm.
Worked. Okay, good.
Yes.
Okay, this is just a line. Are we good with lines?
Yeah.
Now you can do shifting and stuff like that. You could technically see how it's flipped.
Yep.
So it's a negative x, and see how it's shifted up. So
Mhm.
it's really just it's just negative x and then up 2. Or you could have just looked at it and said, hey, look, my y-intercept is 2, and it's a slope of down 1 over 1. So -1 is my slope. Could have done it either way.
Okay.
This one, a dashed line represents the original function. The solid line represents a transformation of f of x. Complete the table. Okay, so the dashed line represents the original and the solid is g of x. Okay, so we're just trying to complete the table here. So the dash, this is dashed right here. So it's the red one. So we're trying to find out where -2, where does it equal -2? Well, here's -2 right here, right? So I'm scanning to the left and I'm looking for where it touches the graph. And it touches the graph right there at -2. You follow?
Yeah.
So -2, -2 is your point. Do the same thing with 0. Where does the graph touch 0? Well, it touches at a couple different places.
Yeah.
You see how it touches 0? If I do this, it touches 0 here and here and here. So they probably want you to write -1 here. And they probably want you to write +1 for this point right there.
Mhm.
Now you don't have to. You could have written, what does it look like? Maybe 2.5. But they probably want you to write +1 for that one. So I'm betting this is 0. Yep, 0, 1. There's that point, 0, 1. And so I bet this is just all up 1. I bet that's 2, -1. Yep, look at the graph. 2, -1 is right there.
Yep.
And then 3, 1 is right there.
Mhm.
So now for g of x, the solid line, I'm guessing it's going to be the same. Is it going to probably be -2? No, it's not. Notice this one starts at 0.
Yeah.
And it's 0, -2. And then it's 1, 0. And then it's 2, 1. So they're just going up by 1 every time. 2, 1 is there.
Yep.
And then it's 3, 0,
Mhm.
4, -1, and 5, 1.
Yeah.
Okay, now they said express the domain and range of each function. What do you notice about the domain and range of g of x compared with f of x? So you can look at, can you not tell by looking at it that it's just shifted right to?
No, yeah, you can tell.
So really the domain and range, it's just going to be shifted, right? The domain of f of x, and notice I'm going to make it a bracket here because it's not a discrete function. It's not just points. There's
Mhm.
actually more than, it's a continuous function. You understand what I mean by that?
Yes.
So -2, 3 is my domain of f of x. And tell me what the domain of g of x is.
Negative. Wait. Would it just be 0, or sorry, -2?
Mm-mm.
It would
No,
be
you were right. It's 0,
0.
5.
Okay.
The domain is from, look at this graph. What's the domain? It's from 0 to 5. This is defined from 0 to 5 on your x-axis.
Okay.
You see that?
Yeah.
And what's the range going to be? Do you remember how to find range?
Yeah. Is it -2 to 1?
Yeah, good job. It's from -2. So it starts here and it ends here if I'm going up from
Yeah.
bottom to top. So, and both of them are the same, right?
Yeah.
So it's the range is from -2 to +1 for both functions. -2 to +1. And what do you notice about them? So you could say the domain, you can say the domain of g of x is 2 greater, shifted 2 to the right or something
Okay.
of f of x, and the range of them is the same.
Yeah.
So it says, what do you notice about each input value when comparing f of x and g of x? Do you see what's happening each time? The output, see how the outputs are all the same on f of x and g of x?
Yeah.
But the inputs are 2 less for the f of x, or the inputs are 2 more for g of x.
Mm-hmm.
So is there any way we can write g of x as a transformation of f of x?
Mm-hmm.
So how can I write that? G of x equals,
Equals, is it just x plus 2 or x minus 2?
so you're going to write f of x minus 2, right?
Yes.
Because that transformation is happening inside there. And if you're not sure, again, plug some things in. If I plug in 0 for x, my g of x, g of 0 would be -2. But if I plugged in 0 to this one, what's 0 minus 2? It's -2. And what's f of -2? It's right here. It's that same thing.
Yeah.
So that's what this whole question was about, is learning how to write one function in terms of another.
Okay. Yeah. Yeah.
You get that?
Mm-hmm.
Let's go back to, did I skip a problem or no?
I don't think so.
No? Oh, that was all of them? Oh,
Yeah.
yeah, I did. I skipped the sine function.
Oh. Yeah.
So this is a sine or a cosine function. It can actually be either one. You could call it a sine function. Now, sine functions always start in the middle and end in the middle. So you could call this a sine function, but this would be your starting point if you were going to call it a sine function.
Okay.
If you were calling it a cosine function, then you can start at a peak or a valley. So actually, this would be easier to call it a cosine function, because then we wouldn't have to shift it left or right. I'll do both for you, but if I call it a cosine function, notice that the typical cosine function starts at the top and it ends at the top, and it goes through like this. That's ugly, but something like that, right? So this is 0, this is 2 pi, this is pi, this is pi over 2, and this is 3 pi over 2.
Okay. Yeah.
That's what your typical cosine function looks like. But what's the difference between this one? Oh, and it would continue, right? Because it's periodic. What's this one doing? What did I do to it? First of all, can you see what I've done? I've shifted it, I've flipped it, and I've also shifted it. I'm going to draw my middle line. Do you see what happened to it?
Shifted it.
It's not shifted. I'm sorry, it is shifted down, right?
Yeah.
You see how this is shifted down 1, 2, 3, 4? It's shifted down 4 units. This is -4 right here. So my normal graph would be cosine of x, but I'm actually subtracting 4 units from it. Now I'm not moving it left or right, so I don't have to mess with that. But what am I doing to the whole thing as well? since it's going, do you see how this is opening down here instead of up here like it would normally do?
Yeah.
So
Yep.
what does that mean I did?
Reflected it.
Over the what?
X-axis.
And when I reflect it over the x, what do I make negative?
The y.
That's right, the y. So your equation is just y equals negative cosine x minus 4.
Okay.
And you can check that if you want. Another way you can check it is just to plug it into your graphing calculator, negative cosine x minus 4. So negative cosine x minus 4, and you can graph it. Boy, that's ugly. You really have to zoom in on this to be able to see the graph.
Mm-hmm.
Like really zoom in. That's bad. All right, let's not use that. I don't like that graphing calculator. Let's use Desmos.
Okay.
This is a good one too. Now you have your graphing calculator would look better than what I just showed you.
Yeah.
Negative cosine x. Did I say plus 4 or minus 4?
Plus 4.
It was plus 4.
Yep.
It was shifted up 4 or down. I thought it was shifted down 4.
Oh, sorry. Yep, you're right. Sorry, down.
It should, yeah. If I wrote plus 4, I think it should have been minus 4.
It's minus 4.
Yeah, there we go. See how it's upside down?
Mm-hmm.
So that's your function. That's much nicer.
Yeah.
Oh, wait a minute. The amplitude is different. Dang it. Actually, I can't even see what this is. Oh, you know what? My bad. That's not 4. That's 1.
Oh,
I didn't see it. That's not 4. That's 1.
yeah.
Do you see that?
Yeah.
So it would not be minus 4. It would be minus 1. And the amplitude, yeah, and that's better because the amplitude, remember the amplitude, it goes up 1 and
Yep.
down 1.
Mm-hmm.
So that means I'm not multiplying it by a bigger number here. If that was bigger, I would have to put like a 4 in front of that or something.
Yeah.
Yeah, that's your answer. Sorry, I didn't see those numbers until just now.
Yeah. No.
Now you could have called that a sine graph if you wanted to. But then if you were going to call it a sine graph, you'd have to shift it to the right pi over 2. So the other way you could call this is y equals, and you don't have to make it a negative sign. You just have to say the sine of, it's going to be x minus pi over 2 because you're shifting it to the right.
Mm-hmm.
And then it would still be minus 1.
Yeah.
Does that make sense? So you could have done it that way as well. So if I take a look at that equation, so if I do this correctly and make it minus 1, there's my graph. And then if I do another one and call it y equals just positive sine, not negative, sine of x, what I say I was doing it, shifting it right pi over 2, minus
Mm-hmm.
pi over 2. Where can I find pi?
Yeah, minus pi over 2.
Yeah, where's pi in this? There's theta. Do you see pi anywhere? Shift.
I
If
don't
I
see
shift
that
it.
in there.
Okay, I don't see it there. Whoops. X.
I don't see it there either. Oh, there it is. It's right there.
Oh, it is. It's right there. Okay. Yeah, duh. So it was x minus pi over 2.
Mm-hmm.
And then Notice that see how it's the same thing, it's just above it. So now
Yep.
when I subtract 1 from it, it's gonna go down right to it. So
Okay.
those two graphs are the exact same graph.
Yeah.
Okay, makes sense?
Yes.
All right. How are we doing on time?
What time is it supposed to be over?
We have 5 more minutes, I think.
I'm not sure.
You know, it's funny, but I've been running around all day, so I don't even know myself. But no one's here yet, so keep asking if you have questions.
Okay. Do you want
Oh
me
yeah,
to?
oh, you know what? Technically it goes to 6:30,
Oh.
and my next session doesn't start till 6:45, but that's okay. Do you have more questions, or was that it?
I think that's really it. All the rest of the ones are just like the same thing.
Okay. Are you getting it okay? Are you doing okay on these
Yeah.
things?
Yeah.
Yeah. It seems like you did. You're not just saying you get it. You actually